Lesson 5-4, Use medians and altitudes. Please press pause and take a moment to copy down the definitions to the 4 vocabulary terms, and then continue the lesson by pressing play. By the end of today's lesson, we will be able to successfully use medians and altitudes of triangles. The median of a triangle is a segment from a triangle's vertex to the midpoint of the opposite side. And it's not necessarily perpendicular to the opposite side. And then if we put in all 3 medians of a triangle, the point in the middle, which is the point of concurrency of the 3 medians of a triangle, is what we call the centroid. The altitude of a triangle is the perpendicular segment from the vertex, so I'll pick a vertex here, to the opposite side of a triangle. Now this perpendicular segment does not cut this opposite side into 2 congruent segments, unless this is an isosceles triangle, which we will talk about later. So if we have the other 2 drawn in, this is just a rough sketch. Pretend this is an acute triangle. This intersection will be called the orthocenter, a point where the lines containing the 3 altitudes of a triangle intersect. Now let's focus in on medians of a triangle. In Theorem 5.8, it states that the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So what this means is that the medians of triangle ABC here will meet at P, which we call the centroid, and AP will be 2/3 of the length of the entire median AE. And the same would hold true for the other 2. So BP will be 2/3 of BF. And OP will be 2/3 of OD. There's a proof on my website. Please go take a look as to why this is true. Example 1, part A. In triangle FGH, M is the centroid and GM is 6. Now we need to find ML and the entire length of the median GL. Since we know by the theorem that GM is 2/3 of GL, then we can substitute 6 in for GM, and then we can solve for GL, the entire length of the median, which is 9. And then how did I get 9? I multiply both sides by the reciprocal of 2/3. And then I can calculate ML by taking GL, which is 9, and subtract that from GM, which is 9 minus 6, and that's 3. So ML is equal to 3 and GL equals to 9. Now part B, suppose FM is 10. By following the same procedure as part A, we can find MK and the entire length of the median FK. So I'm going to go ahead and set my formula up. FM equals 2/3 of FK. So that is just taking 10 setting it equal to 2/3 fk and solving for fk, which equals to 15. So fk is 15. So to get mk, all I have to do is take 15 minus 10, which equals to 5. Example 2, Part A. The vertices of the triangle JKL are given to you. Now I plotted the points and connected the points together to form the triangle. Now we need to find the centroid P for this triangle. Now I'm going to use vertex K as my starting point here. Now if I draw the median down, I need to make sure what the point here is by finding the midpoint of JL. So I'm going to take 7 plus 1, which is 8, and divide that by 2 to get 4. And I'm going to take 2 plus 4, which is 6, and divide by 2, which is 3. So the midpoint here is 4, 3. Now, the distance from vertex K to point M is 6 minus 3, which is 3 units. And to locate the centroid, we're going to have to use the idea from theorem 5.8 that it is 2/3 of the way from K. So that's 2 units down from K. 1, 2, this point. So the coordinates of the centroid P are 4, 6, minus 2, which is just 4, 4. Part B. Where do you need to move point K so that the centroid is at point 4, 5? Well, originally the triangle, well, if you let this be the median, there were 2 units between the vertex K and the centroid P, and 1 unit between the centroid P and the midpoint M. Now, when we move the centroid 1 unit up, then that will increase the distance from the centroid to the midpoint to 2 units. And then we're going to have to find out that how many units will be shifted up, and this will be proportional. So this is going to be 4 units up from 5. So 5 plus 4 will give you 9. Therefore, K should be moved to 4, 9. Theorem 5.9. Concurrency of altitudes of a triangle. Remember that altitude just refers to the height of a triangle. Now we can locate 3 altitudes for a given triangle. And according to the picture here, the lines containing the altitudes of a triangle are concurrent at a point G. Now, this is an obtuse triangle. So the point of concurrency, remember what we call the orthocenter, is located on the outside of this triangle. Now, the lines containing AF, that's one altitude, and BE, which is another one, and CD will intersect at point G, which again, I was just saying that it's the orthocenter. And this is the point at which the 3 altitudes of this triangle intersect. And just for your information, that there are 3 different locations for the orthocenter. If it's a right triangle, then it's going to be located on the triangle. But if it's an obtuse triangle, it's going to be located outside of the triangle. And if it's an acute triangle, it's going to be located inside the triangle. And I'm going to illustrate that in the following. Example 3. Find the orthocenter P in the triangle. If we look at the right triangle in part A, I'm going to outline where all three altitudes are from each vertex. So from this vertex, I can draw the altitude downwards. From this vertex, I can draw the altitude leftwards so that it meets at this point. And from this vertex, I can draw the altitude to the opposite side. As you can see that these three lines or altitudes intersect at this corner, so we can label that P and state that for a right triangle, the orthocenter is located on the triangle. And for part B, we have an obtuse triangle. Now I'm going to show you how to sketch all the three altitudes. So I'm going to look at this vertex first, and I'm going to draw an altitude, or before I draw the altitude, I'm going to have to extend this side of the triangle so that I can stretch my altitude so that it can form a right triangle here. So this would be the height of this triangle from this vertex. And from this vertex, we can just go ahead and stretch the height like this. And then from this vertex, I will need to extend this side. As you can see, all three altitudes intersect outside of this obtuse triangle. So we can conclude that for an obtuse triangle, the orthocenter is located outside. Now for an acute triangle, I'm going to do this really quickly. From this vertex, I can draw the altitude, and this one will be here, and then I'm here. Now, the orthocenter for an acute triangle is located inside. In example 4, we're going to look at a quick paragraph proof. We want to prove that the altitude to the base of an isosceles triangle, so this is the base, and then BD would be the altitude, is a median. Now, in order for BD to be median, we need to prove that AD is congruent to CD. Now, the lengths AB and CB have to be congruent because we're given that triangle ABC is an isosceles triangle. Now, next we can state that angle ADB and CDB are congruent right triangles because BD is the altitude to AC, which was given. And also by the reflexive property of congruency, BD is congruent to BD. Therefore, triangle ADB is congruent to triangle CDB by HL, hypotenuse leg. And therefore we can state AD corresponds with or is congruent to CD because corresponding parts of congruent triangles are congruent. Then D has to be the midpoint of AC by definition. Therefore, BD intersects AC at its midpoint. And BD, segment BD, is a median of triangle ABC. And we will discuss more details in class.